Yeah, perfect. So yesterday we uh, most probably covered till second order delta sigma modulator. Um, so we looked at the noise for both the orders, and we also talked about the behavior of NTF. So then, now that we have seen first order, we move to second order. So then let's generalize the delta sigma modulator, and let's move further by generalizing the block diagram. So then we understood that we need some sort of transfer function in the forward path, which provides us high attenuation at lower frequencies and minimal attenuation at higher frequencies for the noise. So basically, the noise is high pass behavior. So for noise shaping phenomena, we use integrator over here. And then, as we saw, we have a quantizer block followed by the this loop filter, and it is realized by additive noise source along with y. So the output of a delta sigma is nothing but the signal transfer function times u coming from input and the noise transfer function times e coming from noise. So in first and second order cases, we saw that the SCF is basically 1, which means we have a unity feedback from output to input. And for simplicity, we assume that STF is 1 for all cases. It's possible to make a 1 for every each and every case at very low frequencies, and basically within the signal band we can make STF as 1, and then we can say that we comes out to be only U, because STF is 1, so U plus NTF times E. And if this V, this is output of the quantizer, then what can we comment on the input of the quantizer? Basically, quantizer is realized as additive noise source. We have the output of a quantizer, which is this value. So what can we comment on the input of the quantizer? So basically, the input of the quantizer, the output is nothing but input plus E, right? So then we can say that Y, or the input, is nothing but output minus E, or in Z transform way, Y of Z is equals to U of Z NTF minus 1 times E of Z. So how did it, where did it came from? So we have over here NTF times E minus E. So it's basically NTF minus 1 times E of Z, and this is nothing but realizing what is the input to the quantizer based on this relation. So then we have Y of Z equals to U plus NTF minus 1 times E. And looking at this relation or equation, we would be commenting, or let's say what would be the spectrum shape uh, at this point. So how would the spectrum look like? So that's what we are interested in. And E of Z must be shaped by a filter whose response is NTF minus 1. Now, based on this relation, E of Z is not being shaped by NTF, but it's being shaped by NTF minus 1. So NTF minus 1 will also look like a high pass curve. Just the difference will be that the DC gain now will be minus 1 instead of 0. And the key point to observe is that at high frequencies, there will still be a lot of energy or a lot of a noise shaped over at high frequencies. So now we will have our signal over here like this, and at DC, instead of 0, we will be having -1. But we are more interested in the spectrum or the shape at y of n. So, as we know, the input to the quantizer over here is coming from U from a through a low pass filter. I mean, not low pass filter, loop filter or loop architecture. So we have, uh, let's say, a continuous input signal, and which is continuous in levels but discrete in time. And over that signal, we have a noise riding on that continuous levels, and it is basically the noise. So this in total is somewhat the input to the quantizer, which is y of n. So what we can comment on the variance of the noise, I mean this variance, this noise. So like the thing we can comment on the variance of this noise is basically um, um, this from the relation is the noise component, right? This is solely the signal, which is this signal. So we have this relation. So this is the noise component over here. And for first order, our NTF was 1 minus Z inverse. So NTF minus 1 will be just minus Z inverse. And if NTF minus 1 is just minus Z inverse, then what would be the variance of this noise? So basically the mean square value of this noise must be delta square by 12. And for second order, the NTF will be 1 minus Z inverse square. So NTF minus 1 will be minus 2 times Z inverse plus Z to the power minus 2. And therefore, the mean square value of the noise will be 5 times delta square by 12. So we can see, like, I mean, when we move to second order from first order, the variance of the noise at the input of the quantizer increased drastically, like from delta square by 12 to 5 times delta square by 12. So this is something we should notice over here. And I mean, this is the key point to look around over here, because we'll discuss it in more detail further. So if we plot a histogram of the noise which is riding over the input to the quantizer, so basically this. So we have this equation, I mean this relation, and the noise, which is basically NTF minus 1 times E, is Y minus U. So then the histogram of that noise basically is the histogram of Y minus U, and it will be, I mean, that noise also will be a zero mean plot. I mean, that noise will be a zero mean noise. So the histogram plot will also be a zero mean plot. And I would like to demonstrate the histogram as well. So it will be hovering around 0, and we have the bounds. So it is bounded. So this histogram is bounded, and this is a histogram of noise, or basically Y minus U, in a second order delta sigma modulator case. And we have these specifications according to our project. So then um, so basically, I said that it is a zero mean plot. So basically, why a zero mean plot, right? So as I told earlier also, because E of Z has a zero mean. Basically, it's a white noise. So NTF minus 1 times E of Z also will have zero mean. So and also the histogram seems to be bounded because the E of Z is bounded to, we know this from our previous videos. So it is bounded to minus delta by 2. I mean, from minus delta by 2 to delta by 2. And the filter in reality will not be providing infinite gain for all frequencies, but it will basically have a particular bandwidth. It will not go infinity for all the frequencies. So we saw, I mean, for a delta sigma modulator, y of z is u of z plus ntf minus 1 times e of z. So basically this noise part in time domain is represented by the convolution of E of n times h of n minus delta of n. And for simplicity, let's call this h1 of n. And since this, I mean, basically this or this is a convolution, so basically we can say that if k ranges from 0 to infinity, e of k times h1 of n minus k is represent, I mean, it is how this is represented. And this is the expression for the noise which is riding over the input of the quantizer. And we need to find the bound on this expression. And we know E of k, basically the noise, is either equal to or lesser than delta by 2. And that's how this expression is basically lesser or equal to delta by 2 times mod of h1 n minus k. So basically, if we put the bound up or upper bound in this expression, we get this. And this is nothing but delta by 2 times summation of h1 of mod of h1 of n going from 0 to infinity. And here, mod of h1 of n for first order modulator is basically 1, and that of second order modulator, it's basically 3. So when we go for higher order delta sigma modulators, let's say of order 3, so h of n is nothing but 1 minus 3, 3 and minus 1. And as we said, h of n minus delta n is nothing but h1 of n. So basically h1 of n for third order is simply 0, minus 3, 3 and minus 1. So the upper bound on noise riding over the modulator, I mean riding over the signal to the modulator input at the input to quantizer is nothing but 7 delta by 2. So this is coming from here. So then, if we generalize for first, second, and third order modulators, so we have this quantity, which is basically this expression over here. So for first order, it's 1. For second order, it's 3. We saw it over here. And for third order, it's 7. So it's delta by 2, the upper bound, it's 3 delta by 2. And for third order, it's 7 delta by 2. So basically the gain of that noise over a range of pi is 2 times. In second order, it's 4 times. And in third order, it's 8 times, because basically it's the square of omega square, integration of square of omega square. And then the summation of h1 square of n comes out to be 1 in the case of first order, but 5 in the case of second order, and it's 19 in the case of third order. So this is something we should focus on when we are moving to higher orders, because this is something which is increasing drastically. And when we multiply it by delta square by 12, I mean when we multiply this factor by delta square by 12, then we get the variance of noise to the input of the quantizer. So basically in first order we have delta square by 12, but in second order we have 5 times delta square by 12. But in third order, as we move to third order, the variance of the noise to the input of the quantizer is 19 times delta square by 12. If we move to fourth order, it will be 69 times delta square by 12. So it is increasing very drastically. So why, I mean, we need to focus on this, that it is how drastically it is increasing, because we'll arrive at a point where I mean, increasing the order is basically giving us better and better performance. So it doesn't mean that we'll keep on increasing the order. That loops needs to be uh, broken down at some point. And on what basis will it be broken down? So it will arrive at that point. But as of now, we need to focus over here that the variance of the noise is being drastically increased when we are moving to higher order. So basically, as we move to higher order modulator, the in-band noise goes down. Yeah, better performance, yes. And out of band noise is going up because all the noise is being some sort of amplified, but at the same time, it is being pushed to higher frequencies. So yes, the in-band noise is going down, but the overall noise spread over the range of pi, which is the outband noise, is going up, and the variance of the noise riding over the input to the quantizer is also going up. So in general, we have to keep increasing the order. I mean, when we keep increasing the order, we generally end up with an NTF, which is basically 1 minus the inverse to the power n, and in-band noise will be a form which says that the integrated in-band noise for a range 0 to pi by OSR. So that's our band, interested band or the signal band. So the integrated in-band noise is directly proportional to OSR to the power minus 2n minus 1. So basically minus 2n plus 1. For every I mean, this means that for every doubling of OSR, the resolution will be increased by n plus half bits. So this is what we get. And so we can go on increasing the order of modulator for better and better performance, right? But as I discussed earlier, an intuition says that this loop should break at some point. And we have the NTF, which is 1 minus the inverse to the power n. Basically, n is the order of the modulator. And we say, let's say, if we are going to higher and higher orders, so let's say n is a large number, with the motivation being that we want very minimal band noise. As we move to higher order, the variance of the noise at input of the quantizer increases by a very large factor, very drastically. We have seen it. So the outband gain of the noise is 2 to the power n, we saw over here, and the variance of the noise is proportional to the square of that gain. So basically, simply saying that going on increasing the orders of modulator increases the variance of noise to the input of the quantizer very drastically. And we need to keep in mind that the quantizer itself has a finite range, and beyond that range, the output of the quantizer is saturated. So what do I mean by that? So it has its particular range of this quantizer, voltage range. So basically it is having the input range, and the input to this quantizer is basically a signal from a loop filter along with high frequency noise, whose variance increases rapidly with increasing order. So basically, we have loop filter, we have Y, we have seen Y. Y is basically the signal, main signal, and a noise riding over that main signal. And the variance of that noise is increasing very rapidly with the increasing order of the modulator. So basically, we have a loop filter, this loop filter, followed by a non-linear block, which is the quantizer. And we also saw the increment in the variance of the noise which is riding over by, and we also have to keep in check, keep in mind that the quantizer itself has a range, which is basically a voltage range for the input, and beyond or after that range, the output will be just a saturated output, which is of no use. So we have, for our quantizer to be in a working condition, we have to keep the input in this range, and we should not let it saturate. So we need to approximate the quantizer block. So basically the quantizer block is something which is non-linear block, and we need to approximate the quantizer block which introduces the non-linearity in delta sigma loop by a linear block. So in other words, this input to the quantizer is composed of two components. So let's say, as of now, let's consider that this U is DC. Let's say it's DC. So basically this input to the quantizer will be having a DC factor, right? And it will also be having a non-linear factor from quantizer. So this input is composed of basically two components. So one is YDC coming from the DC input, and other one is a shaped quantized noise which is floating around the whole loop. So, but the noise is shaped because we are using the loop architecture. So we have a noise shaping phenomena. So at Y, we do have YDC, but along with that, we have a noise which is shaped. So then let's call it N1. And if output of the quantizer is V, I mean, this is the V which is output for the input YDC plus N1, then we have basically um, a quantizer with output of V and input of YDC plus N1. And if this block was truly linear, so we should do something to approximate the quantizer block as linear block, because we cannot work mathematically uh, in non-linear domain. So, it's very hard working mathematically in while dealing with non-linearity. So, at some point, we have to approximate this quantizer block as a linear block. So, if this was truly linear, then I mean, and if this is the output and this is the input, so for any linear system, the output is related to the input by the constant, by the integers, and the equation for this truly linear system would somewhat look like this. So basically, output can be represented by linear combination of two inputs. So basically, we have two inputs to the quantizer, and this is the output. So it can be represented like this if it was a truly linear system. And by considering V1, YDC, and N1 is provided to us as data, then we could find K1 and K2 by going through the column vectors of YDC, N1, and V, and we can get unique values for K1 and K2. So we have A matrix, we have K matrix. So A times K is nothing but V matrix. So if this quantization block was not linear, then we would have had this relation from here. But along with that, we would also have some error because of non-linearity. So what would be the best approximation of this system to make it a linear system? So in the end, we have to make this a linear system, right? So given that the system is non-linear, we cannot find K1 and K2 such that V is K1 times YDC plus K2 times N1 exactly. So we cannot find, if it was linear, we could have find K1 and K2 very exact. But if it is non-linear, it's not possible to find K1 and K2 such that the linear behaves like this exactly. So then we need to reasonably choose K1 and K2 such that the mean square value of the error is as small as possible. So then we have, if A times K is equals to V, then the least square solution corresponds to this relation, which means matrix A will be, it will be a tall skinny matrix. It's just a way to take the least square solution. And why least square solution? Because in the end we have to look at mean square error, and the mean square error can be given by error transpose time error divided by number of samples. So it's just the introduction to how can we approximate the non-linear quantizer somehow to make it linear. Look like linear, because in the end, why are we trying to do this is it's very hard to deal with non-linear block. So now that we have replaced, I mean, using this technique, if we have replaced the quantizer block by block that is approximately linear, and K1 and K2 need not to be equal. So basically K1 is the gain for DC part and K2 is the gain for noise part, and basically E is the error with zero mean, which is the noise, right? So we can represent the delta sigma loop for a linear approximation to the quantizer by two loops, one which is only dealing with YDC or DC part, and one which is only dealing with the error part, which is basically noise, because E itself is responsible for the N1 part. We have YDC and N1, right? So we can represent it by two different loops just for the sake to make the non-linear quantizer approximate to a linear block. And if the quantizer was perfectly linear, there would be no N1 part and no E part either, because if you go back and recall, this came from the difference of the input and the output of the quantizer itself. And if the quantizer was perfectly linear, then there would have been no E, and as E itself is responsible for N1, there would have been no N1. So basically this kind of analysis where we take a non-linear system and approximate it by its linear part and some error, obviously, is called describing functional analysis. And this is only an approximation where we try and use the fundamentals from linear control systems for solving a non-linear problems. So then, this is just a idea behind the linearized analysis. So then now we will analyze the delta sigma in a linearly analyzed way. So we'll do that in next video. So for this video, as of now, that's all for this video. Thank you so much. And if you have doubts, please let me know.